So if you picture a pristine mountain stream, it looks incredibly refreshing.
Oh, absolutely.
But if you actually cup your hands and take a drink from it, there is a very real chance that nature is, well, actively trying to poison you.
Yeah, it's a harsh reality. I
Mm.
mean, we all have this totally romanticized image of untouched nature.
Right.
We assume that if water is just out there in the wild, bubbling over some rocks, it just must be perfectly pure. But the environment natively contains biological and chemical threats that can do, honestly, severe damage to the human body.
And that illusion that water is just naturally safe and infinitely available is exactly what we are tearing down today. So, welcome to the deep dive. We're looking at your notes on the North Carolina hydrosphere and specifically human water stewardship.
It's a huge topic.
It really is, and the overarching mission for our conversation today is to explore the reciprocal relationship between humans and the hydrosphere. It's this massive, incredibly delicate two-way street. We are going to break down how we impact the water around us and, just as importantly, how that water impacts us.
Yeah, because it is a relationship defined by absolute dependency. When you look at the fundamental constraints of human existence, I mean, we depend entirely on Earth's biosphere for our resources.
Yeah.
But fresh water is a uniquely fragile component of that whole system.
Okay, let's unpack this because your notes highlight a terrifying truth here. Fresh water is strictly limited. It is not an infinite resource.
Not at all.
Because of these massive geological processes that happened, millions of years ago, fresh water is distributed incredibly unevenly across the planet.
Right.
And crucially, a huge portion of these water resources are not renewable or even replaceable over a human lifetime.
Yeah, that timeline is the kicker. When we consume or say we contaminate a deep underground aquifer, it doesn't just refill when it rains next Tuesday.
Right, it's not a bucket.
Exactly. It can take millennia to replenish.
Yeah.
So we are dealing with a finite, non-renewable resource that, as we established earlier, isn't even guaranteed to be safe for consumption in its natural state. Therefore, our good health actually requires constant, deliberate monitoring of the water and taking really highly active steps to make it potable.
Which raises a really fundamental question. If nature itself can inherently be dangerous to us, like if a perfectly natural river can carry dangerous levels of harmful substances, how much of water safety is about fighting nature versus fixing our own mistakes?
See, that is the ultimate tension of environmental science. We are simultaneously protecting ourselves from the environment and protecting the environment from ourselves.
That's a great way to put it.
And because the stakes are actual survival, I mean, guessing is just not an option. You cannot look at a river, note that it looks relatively clear, and declare it safe.
Right, because invisible threats do not care how pretty the water is. We have to analyze hard data to predict its safety. We basically have to take the water's pulse.
Yes, and taking that pulse requires measuring a very strict set of physical and biological metrics. You know the old saying, you cannot manage what you do not measure.
So let's get into those diagnostics. If we are evaluating North Carolina's water supplies, your sources outline a really specific toolkit of metrics we use.
Right.
We are looking at temperature, dissolved oxygen, pH, nitrates and phosphates, turbidity, and bioindicators.
Yeah.
And it specifically mentions macroinvertebrates.
I actually like to look at that list as an interconnected web.
Mm-hmm.
A change in one almost always forces a change in the other.
Here's where it gets really interesting. Think of it like taking the vital signs of a river.
Oh, I like that.
Yeah, like when you go to the doctor, they don't just look at you and say, well, you seem fine.
Right, they check everything.
Exactly. They take your body temperature, your breathing rate, your blood pressure. Environmental scientists are doing the exact same thing. They check the dissolved oxygen to see how well the river's, breathing, and they check the turbidity to see its blood pressure.
Yeah.
They are taking these vital signs to determine if the water source can actually sustain life.
And what's fascinating here is the mechanism behind those vital signs.
Yeah.
These specific physical and biological properties absolutely dictate the types and amounts of living organisms that can survive in that water.
Okay.
Take temperature, for example.
Right.
It's not just about whether the water feels warm. If the temperature of a river suddenly increases, the water literally loses its physical ability to hold on to dissolved oxygen.
Wait, really? Warmer water holds less oxygen.
Exactly. It's a fundamental physical constraint. So if the temperature goes up, the dissolved oxygen plummets.
Oh, wow.
And suddenly the aquatic life in that river is literally suffocating.
That's wild. Let's apply that to another metric on the list then, turbidity.
Yeah.
If I am looking at a river and the water is super cloudy, like high turbidity,
Right.
Why does that actually matter? If it's just suspended dirt and sediment, who cares? I mean, dirt isn't toxic.
It matters because of the cascade effect.
Right.
If the water is highly turbid, it's full of suspended particles. Those particles act like microscopic sponges for sunlight.
Oh, I see.
Yeah, they absorb the heat from the sun, which, as we just established, raises the water
It
temperature.
lowers the dissolved oxygen.
Precisely. Furthermore, well, all that cloudy, suspended dirt blocks sunlight from reaching the aquatic plants at the bottom of the river.
Right, they need the light.
Yeah, so if those plants cannot photosynthesize, they die.
Yeah.
When they die, they stop producing oxygen. So now you have warmer water that cannot hold oxygen and dead plants that are no longer making it.
It's just a total systemic failure triggered by cloudy water. That makes total sense. Now, what about nitrates and phosphates? Because your notes explicitly tie these to the concept of eutrophication.
Yes.
Walk me through that cascade, because eutrophication sounds like a heavy piece of textbook jargon, but I know the reality of it is actually pretty dramatic.
It is incredibly dramatic. So nitrates and phosphates are essentially nutrients. They are plant food. In a balanced system, they are perfectly fine. But if nitrate levels suddenly spike in a body of water, it triggers eutrophication. It causes a massive, unnatural explosion of plant growth, usually in the form of an algae bloom.
Like when a pond turns totally green.
Exactly. The surface of the water becomes choked with thick, green algae.
But if they're plants, aren't they producing oxygen? Like, why is that bad?
It's a great question, but the real danger comes when the algae dies. This massive, unnatural volume of algae has a very short life cycle.
Ah.
When it all dies at once, it sinks to the bottom, and bacteria begin to decompose it.
Okay, I think I see where this is going.
Yeah, that decomposition process consumes massive amounts of dissolved oxygen. The bacteria essentially breathe all the oxygen out of the water just to break down the dead algae.
Wow.
The result is a dead zone where the dissolved oxygen is so low that no human, plant, or animal life can survive.
That is horrifying. A nutrient spike leads to a total suffocation of the ecosystem. Which brings us to the last diagnostic tool, bioindicators, specifically macroinvertebrates. These are essentially the small, spineless bugs and creatures living in the water, like snails or specific insect larvae, right?
Yes, and they're arguably our most honest vital sign.
I kind of see them as nature's check engine light. If you turn on your car and the check engine light is on, you know something is wrong under the hood, even if you can't hear it yet.
That's a great analogy.
With macroinvertebrates, certain species can only survive in pristine water with very high dissolved oxygen. Other species, like certain types of leeches, can survive in heavily degraded low-oxygen water. So if scientists drag a net through a stream and only find the bugs that tolerate bad water...
The check engine light is glaring red.
Right.
You don't even need a chemical test at that exact moment to know the water is sick.
Yep.
The absence of the sensitive macroinvertebrates tells you the environment's capacity to support life has been severely decreased.
So if the water's vital signs are crashing, you know, if the temperature's up, the oxygen is down, and the check engine light is on, we have to ask why. And that shifts us to the other side of that reciprocal relationship.
Human behavior.
Exactly.
Because rivers do not frequently experience massive, catastrophic nitrate spikes all on their own.
No, they don't. Your notes categorize the damage we do, breaking the major sources of water pollution in North Carolina down into two distinct categories.
Right.
We have point source pollution and non-point source pollution. Now, point source seems fairly obvious. It is direct, traceable damage. Think of a scenario where a manufacturing plant has a pipe that dumps industrial wastewater straight into a river system.
Yeah, that's a classic example.
You can basically stand on the bank, point your finger directly at the pipe and say, the pollution is coming from right there.
It's localized, it's identifiable, and honestly, from a regulatory standpoint, it is much easier to manage because you have a single culprit.
Right.
Non-point source pollution is an entirely different beast.
It's the one-off from entire landscapes, right?
Exactly.
Yeah.
We connect this to the bigger picture. When human activities change the Earth's land, which we do on a massive scale, it changes the water.
Yeah.
We reduce forest cover to build cities and roads. We engage in intensive large-scale farming. We dramatically increase the amount of fertilizers and chemicals applied to the land.
So it all just washes away.
Yeah, when it rains, all those chemicals, all that loose dirt from deforestation, all the oil from the roads, it all gets washed across the landscape and drains right into the water systems.
It's death by 1,000 cuts. It is everyone's fault, which makes it, no one's fault.
Exactly.
So what does this all mean? Let me push back here, or at least ask how we manage the science of this. If I'm an environmental scientist and I find a river with incredibly high turbidity and skyrocketing nitrate levels, how do I actually test whether a specific human impact, say a massive intensive farming operation 5 miles upstream, how do I test if that actually caused that change?
Right. How do you know it's them?
Yeah, how do I prove it isn't just a natural fluctuation or an unrelated issue?
Well, you cannot just guess, and you cannot just accuse. You have to engage in what the scientific community calls an argument from evidence.
Meaning you have to build a case.
We have to build an ironclad logical case using the data.
Mm.
You map the watershed, you test the vital signs above the farm, and you test the vital signs below the farm.
Oh, that makes sense.
Yeah, if the water above the farm has a normal pH, high dissolved oxygen, and a healthy population of sensitive macroinvertebrates.
The good bugs.
Right, the good bugs. But then the water immediately below the farm has high nitrates, massive turbidity, and only pollution-tolerant bioindicators. You use that data to prove the connection.
So you use the changing vital signs to draw a logical conclusion and prove exactly what made the patient sick.
Argument from evidence is really the only way we can definitively tie human land use behavior to the degradation of the hydrosphere.
Okay, so we have run the diagnostics. We have used evidence to prove that humans have negatively impacted the water's vital signs, and we acknowledge that the natural environment can also contain its own dangerous substances. The water is sick, it is dangerous, and fresh water is limited. How do we engineer a solution so that this water is actually safe for human activities?
We basically put it through a highly engineered physical and chemical gauntlet.
The water treatment process. Your sources list out the sequential phases of this process: coagulation, flocculation, sedimentation, filtration, disinfection, and finally, storage.
It's quite a journey.
It is, but I don't want to just read a list. I kind of see it as an elaborate, multi-stage security checkpoint. I really want to understand the mechanism here.
Yeah.
Coagulation and flocculation. Wait, what does flocculation actually mean in practice?
Think about the goal. We have highly turbid water full of microscopic dirt, bacteria, and particles that are too small to just sink to the bottom on their own.
Right, they're just floating there.
Exactly. They just float around, making the water cloudy and dangerous. Coagulation is the first step. We add specific chemicals to the water that essentially act like magnets. They neutralize the electrical charges on those tiny floating particles, causing them to attract each other rather than repel.
So they start sticking together.
Exactly. And that leads directly into flocculation. The water is gently stirred, causing those newly neutralized particles to bump into each other and bind together into larger, heavier clumps.
Got it.
These clumps are called floc. We are basically engineering the microscopic debris to stick together into larger masses.
Ah, I see. Because if they clump together and get heavy, that leads directly to the next phase, sedimentation.
Yes. Once the floc is heavy enough, the water is moved into massive, calm basins. Because we engineer the particles to be heavy during flocculation, gravity takes over.
They just drop.
Right. The heavy clumps sink to the bottom of the basin as sediment, and the clear water sitting on top is carefully extracted.
That is brilliant. We just manipulate the water chemically so the dirt gets too heavy to float, so that clears out the major debris. Then we move to filtration, which I imagine forcing that clear water through layers of sand or carbon to catch the incredibly tiny particles that didn't sink.
Yep, you're straining out the last physical impurities. But even crystal clear water can harbor dangerous biological threats.
Which requires the disinfection phase.
Exactly.
This is where we use chlorine, or sometimes UV light, to chemically or biologically neutralize any remaining bacteria or viruses. It's like the final kill switch for anything that could harm us before the water is sent into storage and eventually distributed to your home.
And every single step relies on the previous step. If coagulation fails, flocculation doesn't happen.
Right.
If the particles don't clump, they don't sink during sedimentation. If they don't think, the filtration system gets immediately clogged. It is a strictly sequential safety mechanism.
But as incredible as that engineering is, your notes make a very firm point. Science and treatment facilities are not enough.
No, they aren't.
Good health requires more than just a massive chemical filter at the end of the river.
Because if the water arriving at the treatment plant is too degraded, the plant simply cannot handle it. The chemical load required to fix it would be immense.
You'd need too many chemicals.
Exactly. You cannot rely solely on the facility to fix the water. You have to protect the water before it ever reaches the intake pipe.
And that brings us to stewardship and the rules of the game. We need strict regulations at the local, state, and federal levels. Your sources outline the primary legal frameworks we use in the United States to enforce this stewardship.
Right.
We are looking at the Clean Water Act of 1972, the Safe Drinking Water Act of 1974, and the overarching authority of the EPA.
And these frameworks are designed to manage the human impact we discussed earlier. They exist to legally mitigate both point source and non-point source pollution.
So the Clean Water Act would be the tool used to stop a factory from dumping chemical wastewater directly into a stream,
Yes, regulating that point source.
while the Safe Drinking Water Act establishes the actual baseline standards for what is legally allowed to come out of your tap.
Exactly. But crucially, these regulations also govern land use. As we explored with non-point source pollution, what happens on the land dictates what happens in the water.
Right, the runoff.
So managing the hydrosphere means enforcing rules on agriculture, limiting how much fertilizer can be used, and controlling land development to ensure we aren't completely paving over the natural filtration of forest cover.
You regulate the land to save the water.
It's systems thinking, which honestly, this raises an important question for you listening right now. I want you to truly think about how interconnected this all is. What do you predict would happen if a single land use regulation regarding intensive farming was fundamentally altered or removed tomorrow?
It's the ultimate domino effect. If a rule changes allowing more intensive farming near a riverbank, the non-point source runoff increases. The excess nitrates hit the water.
That triggers eutrophication. The algae blooms, dies, and the decomposition crashes the dissolved oxygen levels.
The lack of oxygen suffocates the macroinvertebrates, completely altering the biological profile of the river. The dead organic matter spikes the turbidity.
And suddenly, the local water treatment facility is pulling in incredibly degraded, highly turbid water, pushing their coagulation, flocculation, and disinfection systems to the absolute limit.
Just to make it safe enough for you to brush your teeth.
Exactly. A change in a farming rule miles away indirectly but forcefully impacts the end user.
Which brings everything we have talked about directly back to you. The water coming out of your tap isn't magic.
No, it's not.
It isn't just an endlessly flowing pipe from a pristine mountain spring. It is the hard-won end result of a massive, incredibly fragile system. It relies on constant monitoring of vital signs, a highly sequential gauntlet of physical and chemical treatment, and strict environmental stewardship.
It takes so much work.
It really does. All of this is actively designed to protect you from an environment that can naturally and artificially become highly dangerous to your health.
It's a delicate reciprocal relationship that requires our constant active participation. Every time we alter the landscape, we alter the water.
We alter the biosphere that we completely depend on.
And that leaves us with a critical concept to consider regarding the data we collect. Next time you turn on the tap, consider this.
Yeah.
If fresh water is a limited, non-renewable resource over our lifetimes, and our land use decisions today undeniably alter the bioindicators and dissolved oxygen of tomorrow, what will the vital signs of your local water supply predict about the humans living around it a century from now?